Well, it's been a rough couple of days. Let's see what day 20 brings us. Looking like a graph, pixels lit in the resulting image. Here's our sample data. We'll go throw that in here. Okay. Seems to be random noise. We combine an image enhancement algorithm and the input image. First section is the image enhancement algorithm. It's normally given on a single line, but has been wrapped to multiple lines in this example for legibility. Second section is the input image, a two-dimensional grid of light pixels and dark pixels. Johnson algorithm describes how to enhance an image by simultaneously converting all pixels in the input image into an output image. Each pixel of the output image is determined by looking at a 3x3 square of pixels centered on the corresponding input image pixels. So to determine the value of 510 in the output image, 9 pixels from 510, 511, 69, 610, 611. Oh, sorry. I read half those numbers. 49 through 611. 9 input pixels are combined into a single binary number that is used as an index into the image enhancement algorithm string. For example, to determine the output pixel corresponding to the very middle pixel of the input image, 9 pixels, squared up, would need to be considered. Starting from the top left, reading across each row, those pixels are off, 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 on, off, 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 on, off. Combining into that by turning dark pixels into zeros, light pixels into 1. That's a binary number, which is 34 in decimal. The enhancement algorithm string is exactly 512 characters long, enough to match every possible 9-bit binary number. First few characters of the string, numbered starting from 0, are as follows. This process can be repeated to calculate. Alright. Through advances in imaging technology, the images being operated on here are infinite in size. Every pixel of the infinite output image needs to be calculated exactly based on the relevant pixels of the input image. The small input image you have is only a small region of the actual infinite input image. The rest of the input image consists of dark pixels. Only a portion of the infinite sized... Okay. More dark pixels extending forever in every direction. By applying the input image enhancement algorithm, you get this. Through further advance in imaging technology, the above output image can also be used as an input image. This allows it to be enhanced a second time. Truly incredible. Now the small details are really starting to come through. After enhancing the original input image twice, 35 pixels are lit. Start with the original and apply it twice, being careful to account for the infinite size of the image. How many pixels are lit in the resulting image? So, let's go see what our real puzzle input looks like. Okay, so interestingly, 0 is on. 0 is on, which means a completely black section, in theory, is on. But at the end, a completely black section turning on should turn back off again. All right, that's a pretty substantial image, I would say. Yeah. All right, so we've been told that this is one big long string, and then there's our input image. Okay, good. Let's go ahead and parse that, right? All right, so the decoder is going to be data sub 0, and we're going to, for each one of those, actually, we could probably leave it as is, right? That's probably fine. Infinite in all directions. Infinite in all directions. What's interesting about this sample data is here 0 is 0. So really what we want to do is we want to say my guess is infinitely off in each direction to start. I'm not 100% sure what the best way to do this is, but we could certainly start by assuming that everything extends out in a particular direction, right? So our grid, so let's say our starting grid, is going to be data from 1, that's a list of strings. So that would be, that's still, right, that'll get us a double character array. And then what we want to do is we want to write transform function that, given a grid, gives us back another grid. So at the very least, we know we need to, the assumption is that everything that we can't see is dark. Small, okay, so the rest of the input image is dark pixels. For the purpose of the example, to save on space, only a portion of the infinite-sized image and input and output images will be shown. So we kind of need to know what the surrounding, what the surrounding stuff is going to be. All right. And I think what we want to do is so our decoder is going to be true and false. Turn that into a list. That should be 0 to 512 lookup. These character arrays these can be Booleans as well, right? So that should be, sorry, that should be there. So that should now be a double Boolean array. And this should be 2 array. So we'll do double Booleans. The interesting thing about the surrounding area is, like, we know the first time through the surrounding area is going to be zeros, but the second time through, the surrounding area is going to be whatever the value of 0 is in the decoder. Because we assume that anything that's 2 away would have started completely dark, and therefore would have been 0. Okay. Does it make sense for these to be arrays? Maybe they should be lists. Maybe it's easier as lists. List of bools. And we'll give you a list of bools. And every time you transform, the grid's going to get bigger, right? Okay. Let's do this. We'll say bool try get value from a list of bool. Grid will take an X and a Y. We'll basically say if X is less than 0 or X is greater than or equal to the grid count, or Y is less than 0 or Y is greater than or equal to grid sub 0 count. We're going to return the surrounding value, right? Otherwise, we're going to return the grid x, y. The next thing we're going to want to do is we're going to want to get trio value. I don't know what's called that. List of bool on the grid x, y. Right. We're going to say for ix is 0, ix is less than 3, ix, iy is 0, iy is less than 3. All right. We'll start with a result of 0. We'll say if try get value on the grid on, actually what we want here is -1 to 1. All right. X plus ix, y plus iy. Surrounding, so this is also going to need the surrounding value. Then all right, so the first thing we're going to do is results shift left 1, result plus equals to 1, and then return the result. What is your problem here? Well, yep, that makes sense. Okay, so this transform, what we want to do is let's say x is less than grid count, y is 0, y is less than grid count. All right, and for every one of these, let's do -1. All right. So every row we're going to do row is a new list of bool. And result add row. And then here we're going to say if y is equal to -1 or y is equal to the grid count, we're going to row add we don't. Maybe we don't need the surround. Yeah, I guess we kind of do need the surrounding. Right, we're going to row add looks like decoder sub-zero. Right? Decoder sub-zero is a bool, sure. And we need to do this for both directions. So what this will end up doing is basically just filling in an extra row around everything based on the zero value, because we know that everything that's outside there should be dark. Is that true? Do we need to go 2? Do we need to go out 2? Alright, I'm going to just... We might. I want to come back to that in a minute. Alright. Decoder of... Get the trio value for our grid, our X, and our Y, and our surrounding. Right? Let's then also do print. All right. So the first thing we'll do then is we'll print our grid, right? We'll print the starting grid. Let's make sure that we have read it correctly. All right, just come over here. That looks like our starting grid, all right. Let's transform it once. First, it's going to be transform our grid. And our surrounding is false. So let's print that first grid. Starting grid. Thank you. All right. So then what we end up having with that now, where's our output? Well, that's interesting. The image therefore looks like, okay, that's the starting image. So this is the first transform. So why don't we see the same thing they do? All right, let's step through our transform. Let's do the get trio value, because that's going to be the interesting one. Let's make sure we've read this correctly. 4, 9, 4, 10, 4, 11, 5, 9, 5, 10, 5, 11, 6, 9, 6, 10, 6, 11. These 9 input pixels are combined into a single binary number. So for example, this is Da 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 da. Right, so let's just go ahead and let's stop that. Whoa. Let's stop that. Let's stop that. Stop that. Let's just do a console write line of get trio value for the starting grid. The X is let's see. So this is going to be 1, 2. It's going to be 2, 2, right? 2, 2 with a surrounding of false. And you want one more of those. 9. How did I get that wrong? This should be 2, 4, 8, 16, 32. This should be 34. All right, well, that's why we didn't get the same grid. Okay. This probably needs to happen here and not there. Actually, no, that can't be right either. No, that should definitely happen before that. All right, let's see. Yes, I know, I could use bar. Thank you. Okay, so if we're going to get 2, 2, then our result obviously starts at 0. Oh, yeah, this should have gone to 2. I already see what the problem is. All right. 34. Fantastic. All right, let's print the first grid. Okay, so should look like this. So that's interesting. So our grid started here, right? So our grid started here with 5 to the left. So this grid starts 4 to the left, which is what I expected. It starts 4 down. Oh, so that's interesting. It starts 4 down. This is me thinking, yes, we needed to go out 2. That's not what I wanted to do. Yeah. Actually, none of that should matter anyway, because our... Right, we should actually be calling this. It's not that we need to go out 2, it's that we should actually be calling this. Yeah, that's what the problem is. Okay, so now our grid looks like their grid. So now if we run it one more time, all right, let's do a, in our print, let's do a quick console write line at the end. All right, and then we'll do this again. We'll start with false. That should get us this. It does. Start with the original input image and apply the image enhancement algorithm twice, being careful to account for the infinite size of the images. How many pixels are lit in the resulting image? So this whole being careful to account for the infinite size of the images makes me feel like they're trying to warn us about this. Because a trio of dark pixels becomes light. Which is why we want this to be decoder of 0. All right. So let's not print. Let's count, right? So Return second. Where, let's see, select many. Select many. That should get us just a straight up list of bools, and we'll say where x is true, and then we'll count. Alright, so that gets us 35 lit pixels, right? 35 lit pixels. Okay, let's try with the real data. See what happens. A big number. Okay. I'm hoping that is correct. Okay. Part 2. You still can't quite make out enough details in the image. Maybe you didn't enhance enough. You enhanced the starting input image in the above example a total of 50 times. 3,351 pixels are lit. Start again with the original and apply the image enhancement algorithm 50 times. So I think what ends up happening is we know that we bounce between fully on and fully off every time. Okay. So let's go back to the original data. Our original input, by the way, fully on to fully off to fully on. So that's kind of interesting, except if it's fully off, it always stays fully off. If it's fully on, it has to bounce back and forth. Okay. Yeah. Okay. I get that. All right. So let's do this. All right. We'll do this. So the grid is going to be the starting grid. For, yes, I know, var. X is 0, index is less than 50. Double plus index. The simple one is going to be grid is a transform of the grid with false. Okay. And then we just return the grid count. So this should get us the right thing for the sample data. 3351. Okay, it does. But I think in my particular data case, like what I want to know is if, let's see, if decoder sub 0 is true and decoder sub 511 is false, and we're going to bounce. And then we always start with surrounding is false. So this will be surrounding. And if we bounce, then surrounding is not surrounding. We'll just say var bounce is that. That's bounce, not bound. Sure, bounce. Okay, still get 3351 again, which is what I should get. But now, when I go to this data, and get a much bigger number. Let's see if that works. It's the right answer. Okay, good. Not too bad today, actually, all things told. Kind of surprising that this was an easier problem than I think. You know, the last few days have been 15, 16. So 15 was kind of crappy. 14, getting a second answer was kind of crappy. Little long on 17, very long on 18, very long on 19. So I'm very happy to have very, very quick answers to all of these. All right, first on the friends board, and third on the work board. Not a big surprise there. I will get bumped down into fourth, probably, is my guess. Again, I think I'm going to end up in fourth at the end of the year on this one, unless I can continue to turn in thirds every time. I might crawl back into third. So we'll see. We'll see how it goes. Anyway, that's it for today, and I'll see you tomorrow.